Good morning. It is really wonderful to see this auditorium filled the way it is. Thank you so much for making the effort to come here today. Today's lecture, next Saturday, and the final lecture on I think it's the 15th, will all be here. So if you found it once, you can find it again. Now, I'm going to accept the blame for what I know many people have been talking about, which is not this lecture, but the lack of coffee. We're working on it, but we're not optimistic. And we've solved so many logistical things. Caffeine has not been one we've been able to solve just yet. We're doing our best. So for those of you who like to caffeinate before the lecture, Small World Coffee is 1 block away, and they make unbelievably good coffee. So caffeinate up. Um, with that, though, I think we can jump right in. So let me switch with you. Maybe it's this one. All right. 1 second. There we go. How do I? There we go. How'd we do on the map? Yeah? All right, we'll take it. Okay. So finally, it is my pleasure to welcome to the Science on. Oh, I'm stepping out. Sorry, Zoom folks. I'll get this. My whole routine is off. It's my pleasure to welcome Princeton University Professor Andrew Houck to the Science on Saturday stage. Would you please give him a warm welcome? So the three questions. You're up. First question, if you would, tell the audience, and here, I'll step out of the way so you've got here. When did you first get interested in science?
Oh, uh, so I was interested in science probably my whole life. And I think the main sign of it was that I like to take everything apart and put it back together. And it started by taking everything apart, and that was the end of the process. But eventually, I sort of learned to tinker and put things back together, and it got to the point that around the holidays, family would come to visit, and they would bring like broken things and say like something's wrong with this, it won't turn on, and I would take it apart and like find that just a wire had fallen out somewhere inside or whatever. And so it was really just a fascination with how things work and how to make them work better. And from there, it took off until I found the particular field that I'm interested in, which I'll tell you about in a little bit.
So, from the time you were a little child to graduate school, tell us about a teacher who had an influence on you.
Oh, okay. There are so many teachers that I could talk about. This was a really hard question. So I remember when I was in second grade, I had a teacher, Miss Yasitis, who was wonderful, and the most important thing that she did was that I had like a cowboy vest that I would wear sometimes, and the days that I wore that, she would only call me Tex, and she would ask where Andrew went, and I thought it was so funny, and it made me just feel good and special. And somehow that has been like a lasting memory. In high school, I had a teacher, Mr. Kavolson, who was my physics teacher. I like that. And he was a wonderful physics teacher. He taught in a way that was not always up at the board lecturing, but it was just a lot of discovery. So do this, tinker with this, figure this out, learn this law. And it was this realization that science wasn't, always just memorization of a bunch of stuff, but it's figuring out and answering questions. And that process I learned, I think, better from him than anyone else.
And last question, when you're not doing research, what's something you like hobby, something for
Oh,
fun, something that's just not sciencey?
something that's not sciencey. Okay, so lots of things. I love to read, mostly fantasy and science fiction. Does that count? I love to hike. National parks are amazing. I play video games. My number one hobby right now is driving my kids to things they need to do. Uh, you know, which doesn't sound like fun, but actually, we have great talks in the car. So it actually is like one of the most fun times of the day is just to sit and chat with people as I drive them to this, that, or the other thing.
Thank you. And Artur? Yeah. So if you have a seat next to you, could you raise your hand? And for those of you in the back who would like to have a seat, please feel free. Wonderful. And while you were finding your seat, looks like we have enough seats for everybody. There's one seat up in the front, one in the second row, one in the third row, one in the fourth row, seventh row. And Anthony, if we can switch over.
Oh, I think switch over to my slide.
Yeah,
I think I'm just supposed to share.
Oh, so just share slides. There we go. And with that, how can quantum computers solve impossible problems?
Seemingly impossible problems.
Seemingly impossible problems.
Okay.
The stage is yours.
Okay. Oh, good. Glad the lights came down because the slides are a little hard to see. Thanks, everybody, for coming out on a Saturday and finding the new location. I was worried that that no one would be here because you'd all be over at PPPL. So that's great. Okay, I want to tell you about the work that's been going on that you may or may not have heard about or seen in the news on building quantum computers. What quantum computers are, how they might work, and to start, I want to tell you a little bit about quantum physics, because there's some weird things in the world of quantum physics that you need to know if you want to actually try and use it to build some technology. And so we're going to start with some very simple thought experiments. So you can imagine I have a piece of plywood. That's plywood. And I have something that launches BBs, pinballs, whatever, big metal spheres, and it shoots it at two slits that I cut in the plywood. And I ask, what happens? So objects travel in a straight line. If I hit the plywood, they just go bonk. They fall down. They don't go through. If they hit a hole, they go straight through. And if I look at a screen as to where they would hit, I see shadows of the two slits. All well and good. If I do this with light, like a laser pointer, and I shine it at two slits, you see something that is different. You see what's called an interference pattern. And I have, if I can make this work, there. So you see, I have a metal film with some slits in it, and you can see that there is a pattern here, which is a series of dots. And depending on the spacing, the size of the dots change. Can everybody sort of see that? I can put it here. There's like lots of dots, okay? Looks kind of like what I drew on the screen. That's called an interference pattern. As an aside, this is like a fantastically useful piece of information. You can use it to analyze small spacing. So crystallographers will shine X-rays through crystals, and that tells them like the spacing of crystal structures. If I like bounce a laser off of my phone, I can see an interference pattern that tells me, do you see all those little dots? That tells me like the spacing of the pixels on my phone. So this interference pattern can tell you lots of interesting information. And what's going on is that light goes through the left slit. It's like a wave. Light goes through the light slit. It's like a wave. The waves sort of radiate out from each of those slits. And when it hits the screen, in some places, I get a high part of the wave from the light going through one slit, a low part of the wave with light going through the other slit. They cancel each other out, and I see nothing. And at some place, I get like high waves from both, and it's a bright spot, and I see light there. And so that's called an interference pattern. It stretches out. Well-known sort of physics that those of you who are taking physics right now in high school probably have started to hear about. So The thought experiment, and it's like now a 100-plus-year-old thought experiment, asks the question, what happens if I do this, but instead of shooting pinballs or BBs, I shoot little particles at little slits. So suppose I shoot atoms, single atoms, launch a whole bunch of them at little slits. What should I see? Will I see shadows or will I see interference? Who thinks I'll see shadows? Who thinks I'll see interference? All of you are lying because you know you should answer the opposite because it's a weird quantum talk. Yeah. So what you see is you see an interference pattern, and this was the first sign of something called a wave-particle duality. It says that particles, even though they seem like little balls, little spheres, little like indivisible objects, they actually act like waves. So if I shoot a bunch of particles at these slits, you can see an interference pattern. The atoms have a wavelength, they can interfere. This is also a sort of very useful technology in and of itself, but that's not the point. The point is that means that atoms going through the left slit have to interfere through this pattern with atoms going through the right slit. But now I'm going to ask you a harder question. Suppose I do this same thought experiment, but now I send my particles one at a time. We know atoms are indivisible. I take one atom, I shoot it at these slits, I wait till it hits the screen. Then I shoot the next atom, goes through the slits, I wait till it hits the screen. Next atom, next atom. Eventually, I'll build up a picture. Which picture do I see then? One atom at a time. Who says I will see the left side? And who thinks I will see the right side? Oh, an even divide this time. So this is where quantum gets weird. In fact, I still see an interference pattern. And that's weird because an interference pattern comes from something going through the left slit interfering with something that goes through the right slit. In order for there to be interference, the atom has to go through both slits, but there's only one atom. And we know atoms can't be divided and without fission-y things happening. There's no fission. So what's going on? Well, this is where scientists say, aha, there's a new principle. Something weird must be happening, and we're going to call this the principle of superposition. And in quantum mechanics, the principle of superposition says that it is possible for an object to do two mutually exclusive things at the same time. It is possible for a particle to go through both the left slit and the right slit at the same time. Now, this seems weird, right? Like this doesn't make sense. It's like saying, when my lecture is done, I might go out that door or I might go out that door. In fact, I'm just going to go out both doors. Don't worry about it. I'll meet you on the other side, right? It doesn't make sense. But, you know, you got interference. It had to have gone through the both things, and it didn't split. So, like, that's kind of the only explanation we could come up with. And so that's what scientists do. You see something, you come up with an explanation, and then, you know, that's your new principle. And it's all fine, but a good principle should be testable, okay? Because if you're going to say something mind-boggling and weird is happening, then it should be able to lead to a prediction that you can test. You can say, okay, I am going to verify this crazy thing I just said. And so we are going to build detectors. Yeah, so these little eyeballs are. They're detectors. And they are going to look and see which slit the atom actually went through. And if it went through both slits, then your detectors should both see the atom going through those slits. It's like, I'm going to park one of you, sorry, I don't need to point my laser pointer at you. I'm going to park one of you in the audience at this door, and your job is to sit there. And if I leave through that door, you say, he's leaving. And another of you sits at this door. And if I go out this door, you say, he's leaving. And if I can go out both doors at the same time, then simultaneously, I will hear both of you shout, he's leaving. because I went through both doors. It should be an easy test to do. And that's how science works. And so we do the test, and in fact, what we see is that the particle obviously only goes through one slit or the other slit. Like, I have to go through one door. Why would you think I go through both doors? Like, that doesn't make any sense. And in fact, when you do the test to test out your theory, you never, ever, ever observe that one particle goes through both slits at the same time. You never see that I leave through both doors at the same time, because that doesn't make any sense. The only thing is, when you do that, the pattern changes and you see shadows for particles and you don't see interference anymore. And this is the second principle of quantum mechanics. When you observe, you change a system. And so, as long as I don't look, I actually go through both doors at the same time. I go through both slits at the same time. And you can see the consequences of that in the interference. But when you look, the system that we say collapses. You observe one or the other of the mutually exclusive events. You can never see both of the mutually exclusive things. But the consequences of having done both also disappear. Measurement fundamentally changes the system. And it's these two big principles: superposition, that you can do mutually exclusive things at the same time, and interference and measurement, that measurement changes the state of the system, that are the backbone of sort of modern quantum technology and the efforts to build quantum computers. I'm going to pause here, see if there are any questions, and then I'll go on. I see a hand. Yes. It's a great question, right? If you can't observe the interference, how do you know it's there? It's because this screen is an indirect way of measuring the interference, right? So you can see the consequences of the superposition, you can see the interference effects, but you can't directly observe it doing both things at the same time. And so the goal when we do this kind of stuff is always to arrange an experiment where you create a superposition, you can see the consequences of the superposition, but you can never quite directly ask the system. You always have to, like, it's like when you want to know something, but you don't want to just come out and ask, and you kind of have to like hint around the edges, and you're trying to sort of find subtle ways to detect the presence of this superposition, but a direct question will always cause it to collapse and change. Yeah. Why particles can be waves? A great question. Why am I sticking to the ground right now? Gravity. But why gravity? Why is it there? Why does it exist? There's no real reason. It exists because that's what we've observed. The challenge with quantum is not that it's any weirder than gravity. The challenge with quantum is that your senses see things at a macroscopic scale. You've evolved to see meter scale, centimeter scale things that are going to eat you probably. And so you build up an intuition of the world where if I throw a ball, it will fall to the ground. If you had grown up in a box in space, not near any planet, and didn't know that planets existed, you would throw something, it would go in a straight line, you would float around, you would have to push things off. And if somebody brought you to a planet for the first time when you were, 20 years old, you would be like, why am I sticking? Why are these things moving in arcs? What is happening? Because you would not have built up the intuition. So what's weird about quantum mechanics is not that it is any weirder. It is just, that's the universe we've given. We've observed it, we've made laws, we understand how it works, and it's no more or less wondrous than anything else. And people always say oh, you're saying quantum mechanics is not actually counterintuitive, amazing, and that's exactly wrong. What I'm saying is that you've gotten used to all of the crazy, wonderful laws of the universe, and you've sort of ingrained them so deeply in your mind that you don't stop to remember how wonderful everything in the universe is. And quantum mechanics, because you haven't gotten to see it before, is a reminder of that. One more, and then I'll keep going. So you have to build up the image, right? So one particle only ever lands at one point on the screen. So when you do these kinds of experiments, and and in quantum, generally what you're doing is you're repeating an experiment many times, and you're building up some probability distribution. And the thing that's changing is the probability distribution that you accumulate over many repetitions of the same experiment. If I did this with exactly one atom, I might see a dot, and that one dot, it could be because of interference, it could be because of a shadow, I don't really know. Until you repeat it many times, you can't know. And in fact, that's a provable thing about quantum mechanics, that you can't, from one single measurement of something, you can't tell me actually what the state it was that it came from. You can only tell me a little bit of information. Okay, one more, and then we're really going to move on. Yeah, so there are things that you can do. You can split atoms deterministically, like in beam splittery things where it's in some superposition. But like whenever you measure it, it causes a collapse. You can cause some delays. You can maybe do some interference stuff before you do the measurement, right? And a lot of what quantum computing is manipulating these states in weird ways before anybody looks at it, so that you can get the information you want out of it. Okay, so quantum mechanics. This is all super cool. This is all like 100 years old. So this is not what's new and exciting. It's just the ground, the foundation for all the weird stuff that we're trying to do with it. This was discovered all in the early 1900s. Why were people studying it? Because people wanted to know how the world worked. That's it. There was no particular technology in sight when people were thinking about quantum mechanics. Which is, how does the world work? But if you don't have quantum mechanics, you can't do this and you can't do this. This is the first transistor that was ever made. It's a pretty big object. It looks sort of weird with like these things, attached to some crystals that are like physically shoved together. If you don't understand quantum mechanics, you don't understand band structure, which tells us how to build a transistor in a semiconductor, and you can't actually make a transistor. We make like 1 trillion of these a second now. So they've come a long way since this thing. And that sort of shows how fundamental ideas lead to technologies, and then they, even though this doesn't seem like a thing that could scale, can be turned into real amazing things. This is the very first laser ever made. Lasers are important because otherwise you wouldn't know which picture I was pointing to. But also, those of you who are listening on Zoom are listening because there's sort of little glass tubes running all around the world with like little pulses of light in them that is transmitting my talk. Anybody who's had laser eye surgery, lasers are ubiquitous. And so two probably of the most important inventions of the last 100 years, the foundation of modern technology, would not be possible without quantum physics. But in their operation, these are classical objects. A transistor is like a switch. It's on or it's off. It encodes a bit of information. It's a 0 or a 1, but it doesn't actually encode a superposition. You can't encode a 0 and a 1 at the same time. And quantum mechanics says that should be possible. And in fact, the field of quantum information started as a thought experiment. It said, if you wanted to build technology like these, computers, lasers, communication systems, and you were limited not by some, math wall, but not by like this thing is hard, but if you just sort of said, what kind of computer does the universe permit if we were bound only by the laws of physics as we know them? For many decades, people thought that this kind of computer is the only kind of computer available. It's called a Turing machine, and every computer that we've ever made, from like old mechanical computers to ENIACs to these laptops to things running AI, they might run different software. They do each step of a problem faster. They might have more memory, but fundamentally, they're all the same machine. And people thought that that was, in fact, the fundamental unit of computing in the universe. It was something like very deep and fundamentally true. until the 80s when people started thinking about, well, what if we introduce some of this quantum stuff? And we found that some of these technologies, you can actually go beyond what we thought was possible if they act in a quantum mechanical way. So 3 principles that are going to lead to 3 technologies. First is superposition. I told you about this with the double slits. This most famously comes up in what's called Schrödinger's cat. Schrödinger's cat, when discovered, Schrödinger said, well, these principles mean that like you could have a cat who's alive and dead at the same time, and we never see that. So this doesn't seem to make logical sense, but it's possible. And so it's his way of talking about the principle of superposition. Now, around campus, people get nervous when I talk about cats being dead. So I just have to assure people the cat is both alive and dead, but the tiger is always alive. Just very clear. Okay. Entanglement. Einstein didn't like this when he called it spooky action at a distance. It says that particles can become connected. 2 particles can be in a superposition together, not just alone, and this allows us to build up more complex states. And of course, measurement. Sometimes goes by the name of Heisenberg uncertainty. It says that observing a system changes or defines reality. And so these are the 3 principles of quantum, and they can lead to different kinds of technologies. So for instance, the idea that a system can be in a superposition says that if you have a computer, you can put the input state in a massive superposition of all possible inputs, and that potentially could give you information that could solve problems. And in fact, we know it can solve some problems that we think can't be solved on regular computers in cryptography, but also in things like optimization, finance, chemistry, healthcare, medicine, trying to think about environmental issues like nitrogen fixing and catalysis. There are problems that just would take billions of years on a regular computer, and if we had a sufficiently advanced quantum computer, we think would take very short, tractable amounts of time. You can use this idea of linking systems to increase our accuracy and resolution when we probe and measure things. You can make sensors that can, for instance, do navigation by measuring magnetic fields, even in the absence of GPS. You can probe biological systems with unprecedented accuracy and resolution. And the fact that measurement changes the system gives you a way of detecting if somebody is eavesdropping on your conversation. And it gives you a way of making provably secure communications that's not sort of secure because some math problem is hard to solve, but it's secure based on the laws of physics as we know them. So there's an enormous possibility for building out these technologies, but of course, actually making them is a real challenge. And that's what I do in my lab. I build quantum hardware, mostly in this field of quantum computing. And so I'm gonna give you a thought experiment on a problem in quantum computing. It's a problem that I think really highlights the difference between advances in regular computing, where you make a computer that's faster, it can solve problems more quickly because it does each step faster, and quantum computers, which are fundamentally different. It's really, I can't stress this enough, the only fundamentally different type of computing we've ever invented. And it solves problems quicker, not by doing each step faster, but by using fundamentally fewer steps. And to illustrate this, I will use what is clearly one of the most pressing problems the nation faces. I will get there in a second. I'm going to say one other thing about complexity of systems, and then I will get to the all-urgent problem. I jumped the gun. Okay, states. If I have 3 bits in a computer, it can encode 8 possible states. Every bit can be a 0 or a 1. Here are all the possible combinations of 0 or 1. And so 3 bits encode 8 states. If I have 3 bits in a quantum computer, then I can be in any superposition of these 8 states. So if I want to describe my 3-bit quantum computer, I actually need 8 numbers. So it is much harder to write down the state of a quantum computer than it is to write down 3 bits, right? I need, each of these numbers needs many, many, many bits to store. And so the ability to describe, to simulate a quantum computer gets exponentially hard. And in fact, if I have n bits, I need n numbers, and those are called amplitudes. And the magic number is 800, right? 800 bits is not even a text message. It's not that much information. But if I have 800 bits in my quantum computer, then I need 2 to the 800 numbers. I need to write down 2 to the 800 numbers to describe that state. And 800 is the magic number because 2 to the 800 is the number of atoms in the universe. And so, if I had an 800-bit quantum computer, I would need to sort of write a number on every atom in the universe in order to actually be able to write down the state of that system. So the fact that it is enormously complex to describe doesn't necessarily mean that it's powerful, but it gives you a hint as to why the systems might be powerful. And now for the all-important problem, I'm thinking of a number between 0 and 3, and I want you to try and guess what it is. Yes, sir. Sorry, I'm thinking of an integer between 0 and 3. What's it? 1! Oh my goodness. Okay, congratulations. That is my number. Literally, this is the first lecture where somebody has guessed my number that I've ever done. How many of you were going to say 2 if I called on you? Like, I feel like everybody always guesses 2 as their first number. Okay, so classically, it takes on average 2 1/4 guesses to get it right. So you have a 1 in 4 chance to get it on your first try, a 1 in 4 chance to get it on your second try, and it really doesn't matter if you get it right on your third try, because even if you're wrong, you know the number. So with 2 1/4 guesses, you can know the number with certainty. If you do this with a quantum computer, it will know the number every single time with certainty after 1 guess. Right? It is a problem that takes fundamentally fewer steps to solve in a way that seems unintuitive. And this simple problem is like the best way to capture how unintuitive that kind of thing is. And the way it does it is it guesses 0, 1, and 2, and 3 at the same time. So it puts in a single guess, but it's a superposition of all the guesses, and it gets back sort of 0, no, 1, yes, 2, no, 3, no. And, that seems like it has every answer you could possibly want in it. It seems like you run the computer once, you get every possible output for every possible input, life is good. And then you look at it to see the answer, of course, when you measure the system, it changes it, and you get one of the things in the superposition randomly, and so you get 0, no, 1, yes, 2, no, or 3, no, but you only get one of those, and that is not useful at all. It's actually worse than classical guessing because you only get one answer to one guess, and you don't even get to control your guess. Your guess is picked randomly, so it's totally and completely useless. So the trick in quantum computing is that you never look directly at the system, but you do something that is kind of like my interference experiment, and the details of how I can't get into too much in this lecture, but you figure out a way to make the no's accumulate a minus sign. They accumulate like the low part of the wave, and the ones accumulate a yes part of the wave, and when you recombine the system, you only ever see the construct of interference. So you use some kind of interference experiment to enhance the probability of the thing you want to see, and you get the answer. I have to hand wave a little. Okay. Generally, this means you can solve certain problems in fewer steps, and it usually starts with a massive superposition. It's almost always effective for problems where you want to know a small piece of information that requires a sort of broad search, right? So, if you need to sort of probe a lot of possible inputs, but you want some sort of specific piece of information, an optimum, a maximum, a period, a frequency, those are the kinds of problems that are useful. Simulating quantum systems in particular is quite good. Okay, so the question is, how do you build one of these? People have been trying to build quantum computers for about 25 years now. And I sort of got into this right as quantum computing became a thing that switched from a thought experiment to something people were trying to do. I heard a lecture when I was an undergraduate here at Princeton as people were proposing the very, very first quantum systems and thought that sounded great, and that's what I wanted to do with my life. And so you have a choice when you start out, because fundamentally there's a tension in quantum mechanics, because in quantum systems, because what you want is you want a system that is isolated, right? Because there's nothing special about people. Anything can come along and measure your superposition and mess it up. And so if anything that passes by can sort of see or extract information about the state of the system, then that's going to effectively measure these superpositions, and that's going to cause them to collapse even though you don't want them to, and that's going to lead to errors in your computation. So what you want is you want something that's like sits in a vacuum and is like impervious to absolutely everything, and nothing you ever do will ever change it whatsoever, which is all well and good, except that you're trying to do computation, which means that in fact you want to put in an input, you want to read out an output, and you want to like do stuff. You want to have steps in your algorithm. You want to have it like run a program. And all of that means you come in and you say, do this, do this, do this, do this, do this. And those commands have to be able to interact with the system. It has to be well connected in order for you to actually do anything. And so almost always people start with one of these or the other of these. So I work in a field called superconducting quantum computing. We build electrical circuits out of patterned metal. These are large objects as circuits go. They are very fast. We can operate them in sort of nanoseconds. They also fall apart quickly. So the very first superconducting circuit ever made, the superposition could last only a nanosecond. And if it takes a few nanoseconds to do an operation, you can't really do much of anything computationally. And so people who start here start with something where you can work quickly, and you have to figure out how to isolate it from the rest of the universe, how to make it last longer. This is my field. This is the kind of thing you see from Amazon, Google, IBM. Almost all of them use a qubit that I helped develop as a postdoc. So this sort of circuitry is really something that's I've been working on for 20 years now. Other folks take something like an atom or an ion, right? This is the technology that powers our atomic clocks. You can think of atomic clocks as like the world's best quantum sensor. Without atomic clocks, we wouldn't have GPS. We wouldn't have any of that kind of stuff. It's also super important for the banking system. Those work on atoms and ions. They're great because atoms are small, not much interacts with them. If you put them in a vacuum, if you put them in a dark box, you can make a superposition state that lasts for minutes. But that means it's very slow to actually manipulate them. And so you have to hit them with lasers, you have to hold them in the right place. You sort of take these atoms and you sort of move them all around. And the technological sort of push of the last 20 years has been starting from something either fast or long-lived, and then figuring out how to either make it faster or longer-lived. These things are up to about a millisecond from a nanosecond, and the operations here are getting faster and faster. Okay, this is just to show things are getting faster. Google and IBM. I'm going to skip that. Okay, this I love this. So this thing here is called a dilution refrigerator. It's like a thing that gets devices down to like a hundredth of a degree above absolute zero. It's a super hyper specialized piece of lab equipment that I've been working on for 25 years. I never in my life thought there would be a dilution refrigerator on the cover of Time magazine. Like, this did not even occur to me as a remote possibility, but quantum is making headlines, and you're going to read lots of things about how we have this, and all of these things are here. And it is true, we now have systems that can do things that you can't simulate on a regular computer, but we can't yet do anything useful. And we're quite a long ways in terms of the size of the systems you need in order to be able to do things useful. The performance of the qubits is still limited by materials. We can't correct errors fast enough to run long algorithms. There's actually a limitation on how many qubits you can fit in these systems, so you need to figure out how to make this modularized to go bigger. And honestly, we don't know exactly what we want to do with these near-term quantum computers. Almost all the things we know how to do with quantum computers are like, if you have 1 million qubits, you can do this, and it's wonderful. IBM's hardware has 150 qubits. Google's has 100 qubits. 100 is a lot less than 1 million. And of course, we need lots and lots of people working on the field in order to make it happen. At Princeton, there's an enormous collection of folks working on quantum information science in different ways, and it's really a sort of full stack challenge. And I want to put this out there for all of the students in the room. Regardless of what part of physics or science you like, there's a place for you in this stack of how to build these quantum technologies. So in terms of materials, chemistry, and material science, there's entirely new questions, right? So there's a a push to find new materials that might make qubits that are immune from noise. This is what Microsoft is working on and has trumpeted recently. We have Professor Ali Yazdani who works very hard on trying to find materials like that. There's a question of, can you take conventional materials and make these superconducting circuits or other qubits immune from noise? What actually kinds of defects in this thing are actually the source of loss, and can we get rid of them? And of course, at PPPL, which is not where we are, but if we were there, here at PPPL, people work on growing diamond with plasma-based technology in order to make exquisite quantum sensors that can measure things, designer quantum materials. How you encode the information, there's lots of different ways to do it. People make electric circuits where there's little electrons that are held in place that can encode quantum information. I work on superconducting circuits. There's a number of faculty who build grids of atoms. So every dot you see here is an atom that's held in place by lasers, and grids of atoms held in place by lasers is one of the leading ways to build these quantum systems. You have to figure out how to put them all together. That's the world of computer architecture and error correction. How do you take a small number of devices like that single transistor I showed you earlier and put them together to actually do computing? There's an enormous amount of classical control, packaging. How do you put all this together in a way that keeps it immune from the world? How do you actually build the classical hardware that can control all of these systems? Those are not actually easy challenges. And of course, in the world of applications and algorithms, like, what do we actually do with it? Are they going to do anything soon? Are they going to do anything ever? What can we do with it? This is really the full stack of quantum science. And it's even more complicated because there's all of these different physical systems. You can build computers out of atoms or molecules or electrons or diamond, and they all have sort of different things. You can work and experiment in theory, and so you get this like enormously complex world of people who have to come together and work together. And as scientists, no single person can do this alone. So a lot of what we do is figure out how to connect people with different pockets of expertise and get them to work and talk and collaborate in a way that can sort of navigate up and down, in and out, left and right, create this stack. And of course, a lot of that is one of the things we do at Princeton, which is education and training. It's a hard problem. If I just think about the requirements for what this would look like, we care about electrical noise. So the signals that I measure in my lab are about 1/1 billionth as strong as the microwave signals that you get on your cell phone when it gives you like 1 bar and you can barely do anything. So really, really, really weak electrical signals. That means that like when people plug something in a lab next door to mine, I generally see it, and it's not the best. Temperature matters. If you're in a lab and the temperature changes by 1/2 degree, well, it's probably everything's out of calibration. So you need exquisitely temperature-controlled systems. Vibration. We care a lot about vibration. We're often doing things with atomic level precision, and if the system is shaking around, if you imagine that like grid of individual atoms like shaking, if somebody comes and bumps the table, that can mess everything up. And we're building devices where we really care about every atomic impurity in the system. And so this requires all kinds of new facilities. If you happen to see there, a fence went up near the soccer stadium. There's a new quantum building that's going to try and help address all of these kinds of challenges. It's not just a building. It's also coming together in other ways. I point out that the Department of Energy was sort of tasked with building National Quantum Initiative research centers. So Congress passed the National Quantum Initiative Act over 5 years ago now, which established 5 big national research centers in the Department of Energy. I direct one of those 5 centers. PPPL is a partner in that center, but it brings together companies, 5 national labs, 20 universities, all working in different parts of this. And these sort of big centers are critical for sort of combining the kinds of knowledge that people need to have in order to make this happen. And of course, at Princeton, we are also investing heavily in quantum. It's one of President Eisgruber's top priorities, figuring out ways of bringing the very best people in the world who also want to collaborate and think broadly about science, building the most technically sophisticated physical science building in the world, but also making sure that it creates the kind of community you need to do science and the kind of tools that can do things with atomic level purity and precision. So all of that will help with this quantum computing making headlines. We're getting better at all of these things, but I just want to highlight this last one because that's where you all come in, students. Regardless of what part of science you find most exciting, the fact that you're here says that you find science exciting. I hope that this grand mission of trying to build devices that keep their quantuminess through the outputs is something that is exciting to you. And regardless of what you study, there is a way that you can join into this effort. And really keeping amazing scientists coming with new ideas and new energy is the most important thing for actually making this a reality. So thanks, and I'm happy to take more questions.
Thank you, thank you, thank you. Microphones are coming on both sides. And as always, if you just raise your hand and wait for the microphone so the folks online can hear you.
What is the relationship between NP and P compared to quantum computing? And for those who don't know, NP is non-probabilistic polynomial computation, and P is a polynomial. Basically, NP universe would end if you had it computed normally, but it could be done very quickly if you could just, in NP language, just like in quantum computing, you talk about guessing all the answers at once.
Yeah, that's a great question. So computer scientists like to think in terms of what are called complexity classes. So you can quantify how hard a problem is by how many steps it takes or how much time it takes to solve as the problem gets bigger, or with lots of other different ways of thinking about it. And so one class of problems that we sort of think are sort of colloquially the easy to solve problems are called P. There are harder to solve problems that are, well, there's a broader class of problems which include harder to solve problems called NP. A big open question in computer science is, are these actually equal? Is every problem easy to solve? We think the answer to that is no. There are similarly ways of classifying problems for quantum computers. So there's a class called BQP, which are problems that can be solved on a quantum computer in polynomial time with a bounded probability of error. Those are what we would say are easy problems for a quantum computer. A quantum computer can definitely solve everything a classical computer can, so P is inside of BQP. We also know that there are certain problems that we have no idea how to solve efficiently on a quantum computer that can be solved, don't know how to solve on a classical computer that can be solved on a quantum computer, like prime factorization of numbers. So we think that BQP is bigger than P. None of this is ever proven. These are just where everybody really, really thinks is true. We also are pretty sure that a class of problems called NP-complete, which are a bunch of important problems that are all equivalent to one another, are not solvable efficiently on quantum computers. So we think that not every problem that is hard or desirable can be solved on quantum computers, which is good in some ways. So one of the things that happened in the past year is that NIST announced a bunch of what's called post-quantum cryptography algorithms. So one of the scary things about quantum computers is that they're particularly good at breaking cryptography, breaking codes. So I can get all of your credit card numbers once my lab, which that's how we're going to fund the new building. Actually, it's not great, right? We rely on information security in the country, and we need to make sure that there's some cryptographic things. Now that we know that there are problems, or we think there are problems that quantum computers can't solve, we are building up cryptographic systems around those problems that will be immune from attack on a quantum computer. And so really understanding what is and isn't solvable is great, both for finding applications and for making sure that we can continue to communicate securely.
There's a question back to your left.
So I was wondering if all the calls for the quantum computer are going to be to regular computers, because it makes all the calls at once, would that end up slowing the processing down, or would it be like that it just takes from multiple other computers or multiple other databases for every single one of its calls? Like, how would you support the quantum computing in that way?
Yeah, that's a great question. So it's really about the interface between classical and quantum computers, right? So a quantum computer is really great it's controlled by classical computers. So in some things, a classical computer, it needs to know the instruction set. It needs to know how to manipulate the quantum computer, even if it doesn't know what the quantum computer knows. The quantum computer stays in some big superposition state. But if there needs to be a regular back and forth interface, then that has to happen through a classical channel, right? So the classical computer basically has to measure something about the quantum computer and act on that. And so that's always one of I always think of it as, this quantum world is this exponentially big sort of universe of complexity, and you get to like poke at it through these like teeny tiny little pinholes. And so the art of designing a quantum algorithm is figuring out how to sort of figure out exactly when you want to get that one bit of information in or out. And that means that certain problems really seem like they won't be solvable on quantum computers. If your problem is something that is like relatively simple computation and lots of input and output, that doesn't feel like something that really is the right thing to do on a quantum computer. So quantum computers are not going to solve all of the world's problems. They can solve certain problems that we don't know how to solve in any other way. But some problems, they're not any better than a classical computer, and they're slower and more expensive. So you would just use your regular computer.
Other side of the auditorium, there's a microphone. There you go. You just hold it up.
Thank you. Two questions. The first is, what type of collaboration are you doing with the hyperscalers? And the second is with Doge. You just implied a funding that was established in 2020. Do you foresee impact to your research budget?
So sorry, what was the first question? What is the
collaborations with the hyperscalers?
Hyperscalers?
Google or Amazon?
Yeah, right. We collaborate really well, right? So this National Quantum Initiative Center I run is really a three-legged stool. It's a collaboration between academia, industry, and national labs. And they all have a different style of research that dovetails nicely, and all of them are necessary. So industry is great at building large-scale systems, but everything that industry puts into their quantum computers was really developed in an academic lab. Academics are much faster and more innovative. We can change course much more quickly and generate sort of risky new ideas that change the trajectory of industry scaling. And national labs have this sort of really incredible infrastructure for measuring the kinds of things we need to measure. We use the National Synchrotron Light Source at Brookhaven National Lab. That's a sort of billion-dollar instrument that's shared by scientists around the country for probing materials. And those kind of tools are essential and obviously can't be set up in a university alone, and also aren't something that a company is going to build. And so this sort of partnership is actually something that's really accelerating what we do. Funding. The quantum information is something that I think has bipartisan support. So I don't think anybody is out to get us. What we do is really important for national security. It's really important for economic security. Every party has always supported us well. I think there's some nerves on the impact on universities in general. I think a lot of people don't understand the kinds of investment that our endowment at Princeton enables. For instance, we are building a giant new quantum building that's really from the endowment and hopefully from donor support. We have faculty, we have equipment, we have facilities, and sort of as people get nervous about the funding climate, everybody gets a little bit more cautious in their ability to invest. But we rely on government support immensely, because that is how we hire all the people who do the hard work. We rely on the university endowment and the university investment, and I hope it continues, because it's absolutely essential.
Other side of the auditorium, right in the middle.
On average, what would you say is the power consumption of these quantum computers? Because I know with large language models, they're looking at, say, like nuclear fusion, because it would be able to supply the energy for these large systems. So in the case of quantum computers, if we're able to make it, whether it be commercial or it's able to have an application, what would be the power consumption?
Power consumption is very high in most of these systems. Usually we're using a lot of power to cool these refrigerators down. Each of these dilution refrigerators runs on 5 kilowatts. So it's quite a bit of energy to get things cold. The people who are doing atoms have lots of lasers that they use that need to trap things. So these are not, nobody is building out energy at the sort of machine learning data center scale yet. But quantum computers are not going to be hyper energy efficient in total power. Now, for problems that can run on a quantum computer and can't run on anything else, they're infinitely more energy efficient because we just don't know how to solve some problems on regular computers. But they're not sort of ultra low power devices.
Back to the auditorium. There you go.
Hi, thank you so much. Very interesting and fascinating. And I have a lot of questions, but I'll restrict it to 2. So the first one is Microsoft just came out with this announcement of their quantum computer. I want to understand the science behind that announcement and your perspective in terms of how you would rate it in a scale of 1 to 10, of whether it's the scalability of it, the use of it, the hype around it. So that's question number 1. Question number 2 is, I've heard a statement saying that blockchain, which is unbreakable today, will most likely be breakable with quantum computing. And I wanted your perspective on how you think of blockchain as well.
Sure. Okay. Microsoft had an announcement on Majorana 1. There's an approach that many in the field have been using called topological quantum computing. And the idea is you can create a new kind of particle that is robust against observation if you don't want to observe it, and therefore wouldn't have the kind of errors that we're fighting against in quantum computers. Those particles themselves are actually quite fragile, so even though the information doesn't decay, the particle can actually fall apart, and then you lose the information anyway, though not by direct errors. So people have been trying to do this and have made various claims that they think they've seen it, and then they haven't seen it, and they think they've seen it, and they haven't seen it over the last 15 years. Microsoft had a nice paper that came out in Nature that said that they saw evidence that they maybe are seeing this particle, but they don't yet have evidence that it's topological or that they can do computation with it in the scientific paper explicitly. The press does not quite match the claims specifically made in the scientific paper. That's a thing I think we see actually across all quantum computing companies, is a tendency to oversell what they have in terms of practicality compared to what actually the really nice scientific work that's been done is, right? I would say, clearly Majorana-based devices are well behind where all the other platforms are. They have not yet even demonstrated a qubit, let alone systems of qubits. But there is a chance that in the future, that could be a technology that scales more efficiently, right? So it could be that one of these systems that's going today, atoms or superconductors, will do amazing work for 25 years, and then in 25 years, the topological-based systems are better, right? We had vacuum tube computers before we had silicon transistors. It's not always the case that one technology is the answer always and for all time. It's still very early for that technology. For blockchain, I think it depends a little bit on exactly which thing we're talking about. Different cryptographic protocols are more or less robust to quantum attacks. So I think it really depends on how you're thinking about the cryptography, and that's a sort of more complicated question.
Back to the other side of the auditorium. I don't see the microphone though. There we go. You see it in the middle. In the
Where
back.
are we at?
Right. So AI has been rapidly growing, and so have quantum computers. So are we able to combine AI and quantum computers further?
Yeah, so it's a great question. There are sort of 2 ways you could think of that, right? There's AI for quantum, and then there's quantum AI. So AI for quantum is something that's happening right now, right? You can use AI to make the control of a quantum computer more robust, to design a system that's more robust. So AI as a tool to manipulate quantum computers is clearly there. There's a bunch of theoretical work that suggests that combining quantum and AI might actually make something that's even better, but it's not it's claimed. There are maybe edge cases where I kind of believe it. I don't disbelieve it. I don't think they've proven the case. So I think that remains to be seen.
Back to the auditorium, way in the back.
Would you yourself focus on topological qubits?
Well, I mean, I have a giant superconducting qubit lab at the university. So, now what's interesting is the ideas of topological quantum computing have given rise to a way of correcting errors in superconducting quantum computing called surface codes, where you basically build this sort of artificial sort of pseudo material out of your superconducting qubits that kind of mimic some of the ideas of the topological quantum computers from materials. But if I really thought that topological quantum computing was the way to build a quantum computer, I would stop working on superconductors and work on that. The joy of being an academic is you can, at any point work on anything you want. And I'm still working on superconductors.
Go ahead, right there in front of you. Put the mic. There you go.
So you were talking about the Microsoft headlines and stuff. Regarding the recently announced new state of matter.
Yeah.
How does that relate to the current states of matter, and what would phase changes to that and from that be like?
Yeah, that's a great question. So, the normal states of matter we like to think about are solid, liquid, gas. Sometimes people will throw in plasma. Those are sort of bulk states of matter. People in physics have been thinking about more exotic states of matter for quite a few decades now. And I would say there's by some definitions, hundreds of states of matter. And the way you think about it, a state of matter is you say, if I have some particles and they interact in some way, what are they going to do collectively, right? For sort of normal matter in the real world, there are the three normal states. But you can also sort of put them in a very confined system and make very, very controlled types of interactions between them, and then change some parameter. And if you change some parameter, a magnetic field, a temperature, whatever you feel like it, then suddenly the behavior changes. And we call that a phase transition. And sometimes you see things where stuff acts like ferromagnetic, or it acts superconducting, right? So there's a phase transition from electrons sort of moving with resistance to superconductors. There's all kinds of different phase transitions. So this is sort of a new kind of phase transition where you go into this collective behavior where a whole bunch of electrons are acting together, and sort of one easy way to understand it is not like it's a whole bunch of electrons that are each individual electron is doing this and that and the other thing, but collectively the electrons are acting like a particle. And that particle is called a Majorana fermion. But it's really the action of a whole bunch of electrons sort of working together. It makes more sense to call this a podium than some carbon atoms and some electrons, right? It's a thing. And it's kind of like that. And so, and it's actually really an amazing field of physics. That field of physics is called condensed matter physics. And it's kind of the opposite of the particle hunters, right? So there's a whole bunch of people who are really interested in fundamental particles, and they take things and they smash them and they break apart, and then they smash those and they break apart. And the question is, as you break things down into all the, what are the smallest pieces and how many particles are there? And what's amazing is there's very, very, very few fundamental particles and very, very, very few forces, so ways for them to interact. And so the condensed matter people are the opposite of those guys. They're the folks who say, now, how do you get the enormous diversity of matter that we see in the world arising from so few fundamental particles and so few forces? You turn on a couple interactions and a couple particles, and suddenly new things emerge. And these new states of matter are different ways of thinking of the stuff that can emerge from all of these individual simple pieces.
Right in the front row.
Do quantum computers shed any light whatsoever on the potential existence of a multiverse?
It's a great question, actually. There's a perfect interpretation of quantum mechanics, which says that instead of systems collapsing. When you measure something, the universe splits, and you have sort of parallel universes where each sort of different thing happened. There's another way of thinking about that, which is like, if I look at something that like went through that door or went through this door, and I look at it, instead of saying like the system collapses, I've now entered that superposition. I'm part of that superposition, and now I'm entangled with it. And there's like me who sees person going out that door and me who sees going through that door, and we sort of are now in a superposition. And every time something is observed, the superposition grows, and the observer enters that superposition, and nothing ever collapses. And that is a totally mathematically valid thing that's actually been formalized by quantum information theories. You can show that any sort of observation can be thought of as entangling the system in a larger and larger space. People sometimes refer to it as going to the church of the larger Hilbert space, because it's sort of this like almost mystical view of the world. The version of quantum, and all of these are experimentally identical, and we can't think of any experiment that can distinguish between those. And so you can think of it in any way you want. I don't actually know any physicists who really believe the view of superposition and measurement causing superposition to end. That sort of is the people sometimes refer to it. It's called the Copenhagen interpretation of quantum mechanics. People sometimes refer to it as shut up and calculate, because it's sort of something that I don't think anybody fundamentally and deeply believes, but also is the absolute 100% best way of doing quantum mechanics if you actually need to know an answer.
Right in front of you, there's a student. Lift your microphone up. There you go.
Can quantum computers generate formulas?
Can we generate formulas? So you need to ask it the right questions so they can maybe help you in deriving a formula. There are some algorithms on quantum computers that can solve a certain type of equation called a differential equation more efficiently than a regular computer. And so if you have a set of equations and you need to solve or simplify them, quantum computers can do that. But they don't just sort of pop out formulas out of the blue. You have to ask just the right question. Great question.
Back to the front row.
Yes, as quantum computers evolve, do you anticipate that they will continue to require the absolute controlled environment that you described?
Almost assuredly. We don't know. We don't know any approach to quantum computers that don't require some of the things I said: electrical stability, ultra low temperatures, vibration stability, things like that. So I and every person who's ever said anything like this in the history of science has come to regret it. Don't see personal quantum computers as being a thing that will ever exist. But and this is being recorded too. Wonderful. But I think there's a good motivation for it now, which is that you don't touch even like the tiniest fraction of the computing power that you use in your life. Like, I think it's something like 99% of the computing power you use sits in some data center somewhere. And all you need now is a good enough computer that can talk to that and have it solve the problem. And so I don't think there will be a drive to make personal quantum computers that are quantum-y and sitting in your office because you could just have a computer that talks to the quantum computer in some highly controlled data center somewhere.
In the back of the auditorium.
I know you talked about physical limitations and quantum computing needing to get better. Are there any aspects of quantum computers that we have now that can help it almost self-evolve and work out its own problems?
No, that's a fascinating question. And in some sense, we always do that because when you build a 100-qubit quantum computer, you figure out all of the things that you didn't think about before, and that tells you, in some sense, a quantum bit is the best probe of its environment that we know of. And so you can think of a qubit as a spectrometer, as something that measures noise, and that is what guides us in figuring out how we make the next generation of quantum computers better. And so they're not yet solving problems. explicitly, but they're probes of the things we need to solve. I think we might enter an era where quantum computers could start to provide some kind of guidance, but I think that's going to be a little ways off, or good ways off.
In the front, okay.
My question is back to wave particle. Is there any entity, any concept, any numbers we can point to said, as far as this is concerned, wave or particle are both okay?
I think everything we can say, wave and particles are both okay, right? So
you were saying that, I think the way you phrase it, we seem to put classical physics and quantum physics in two different worlds, then communicating. Is there a common ground we can say, as far here is concerned, they're both okay?
Yes, right. I mean, I think it depends a little bit on exactly what you're doing, right? So, for instance, light, we always say is a wave, but we also know light is quantized in discrete units called photons. Light has momentum, so it can act in ways that we normally associate with particles. I think matter normally acts in ways that are associated with particles, but we can see in certain regimes things like interference effects. And so a lot of it has to do with exactly what is measuring the object that you're thinking about, right? So, when you're asking sort of, where are you? Where is this atom? Those kinds of questions are sort of setting matter to look more particle-like. And so depending on how it's interacting with the environment, the sort of particle or wave description makes more sense. But, in the classical world, particles act like particles and waves act like waves. And so there is something that we don't really get, right? And there's this sort of crossover from quantum to classical where objects get bigger and bigger and bigger, and these quantum effects still underpin everything, but they kind of get washed out, and then everything acts classically. And there's sort of some times that we kind of can draw how that works, but a lot of times we don't really know how that works. Like that sort of evolution as things get bigger to classical physics from quantum physics is a little bit fuzzy.
Go ahead, in the back of your turn.
Could you talk about the state of the art of quantum algorithms? What problems look like they're closer to being solved than others? And since this is being recorded, could you add by when?
Could I add what? Oh, yeah. I think we are getting better at building quantum computers that can do stuff, right? So right now you will read frequently in the paper, I think, true claims that so-and-so has solved a problem that would have taken 1 billion years on a classical computer. Almost all of those problems are essentially random circuits. So the idea is you do a bunch of random things on your quantum computer, and then you ask the quantum computer, what's the output of that set of random things? And you do that over and over, and you get a probability distribution of the output. And the quantum computer is really good at predicting what a quantum computer will do when you do random things on a quantum computer, as it turns out. It's sort of an algorithm. It's like, what are you going to do if I do this? And because quantum computers are, it takes so much information to write down a quantum state, if you have enough quantum bits, it's very hard to build a classical computer that can predict what the quantum computer will do when you do random stuff. And that's essentially what everyone has done when they say, we've done a thing that would have taken billions of years. It is true. It is not useful. Okay. So I think the next step is to maybe get to things that are interesting, right? So there might be some problems that are maybe not practically, commercially useful, but can maybe solve interesting science challenges and science questions. And I think we might start to see those in the next 5 years. Those are often simulating quantum systems, simulating something in chemistry, simulating something in nuclear physics. And those are problems sort of fundamentally in their DNA have quantum mechanics, and it shouldn't be surprising that quantum computers are good at solving problems that are fundamentally good at quantum mechanics. There are problems like simulating molecules that I think could be potentially useful, for things like catalysis. I think that's where a lot of people are predicting the first maybe actual useful, commercially viable algorithms coming from, because the molecules people tend to use in catalysis are small, and so they're the kind of things that might be able to be performed on early stage quantum computers. There's also a lot of uncertainty, right? You know, a lot of what we know in computer science is good and works in terms of optimization are things that don't work all the time. You can't prove that they work. There are cases where they don't work, but they're still useful, and those are called heuristics. And there's a whole bunch of things in quantum computers in terms of optimization that, you know, when you get a big enough quantum computer, you might actually get some interesting and useful simulations, data, solutions out of it that might not be absolutely perfect. It might not work all the time, but it still might be better than what we can get classically and useful. And then, of course, to do anything on a full-scale quantum computer, you're talking sort of millions of qubits, and that's going to be, you know, probably a decade at least, if we're optimistic.
Back to the front row.
What is the material technology you're using to make qubits? That's silicon and gallium arsenide.
So people use different things. My lab, we have patterned metal on either silicon or sapphire substrate. So it's tantalum and aluminum patterned on silicon and sapphire.
Right in the middle. Yep, raise your hand up.
Hi, I have two questions, if that's okay. First, you mentioned earlier in the lecture a sort of a magic number of 800 qubits, and how that would require you, in order to write down the amplitudes for those qubits, you would have to write them on every atom in the observable universe. So, is that a real, actual, solid barrier, or would we be able to make a computer that has more than 800 qubits?
So sorry, a quantum computer stores its own information perfectly if we make it. So a quantum computer doesn't face that limit. My analogy was, if you wanted to do a brute force simulation of a quantum computer on a classical computer, the amount of memory you would need exceeds the number of atoms in the universe. So if you're trying to do a brute force simulation of a quantum computer on a regular classical computer, and you are making absolutely no approximations whatsoever, there's nothing, there's simply no way around that. Now, you can make approximations to simulate a lot of things reasonably well, but you're sort of cutting out some information, right? Like, I can simulate dropping a ball and it hits the ground, and that simulation works perfectly because I'm ignoring almost all possible degrees of freedom. And so that's not to say you can't simulate anything, but you can't do the absolute full perfect quantum simulation on a classical computer.
See, thank you. And then, as I guess our body of knowledge, physics, grows at the rate that it does, whether that's fast or slow, do you foresee there, or would you be open to believing that there'd be a time in the future where some new development in physics would eventually allow for the creation of yet another kind of computing that's uniquely different from both the classical computing we know and the quantum computing that you've described?
I like the way you think. That's a great question. And as we discover new physics, we discover new laws of physics, then we have to rethink everything we thought about constraints on technology and what we can do. And it is entirely possible that we are only seeing some small sliver of the laws of physics as we know them. Every time we think we've discovered all of physics, we discover everything we know is actually just an approximation of something bigger. And once you understand that, then maybe there's more you can do that we previously thought was impossible.
I think we have time for one more question. I saw the microphone. There it is.
Thank you. You mentioned about the interferences while building superposition, like electrical interference, vibrations, and temperature. Do you think space is the candidate for conducting these tests? Has there ever been some idea floated to run these tests in space? That's one question. And I have another basic question. Is the mindset for quantum computing just binary, this or that, or tertiary, or as multiverse possibilities exist?
Sure. Good question. So one, would we put a quantum computer in space? I would say definitely no. And the reason is that one of the other things that comes along and hurts our quantum computers are cosmic rays, and they don't hurt us at a rate that is absolutely killing quantum computers right now. There have been some experiments that have shown that if you put a quantum computer deep underground, it can shield you from cosmic rays, and then that solves the problem. If you put it in space, that would make the problem a lot worse. And I don't think there's enough that you could win that would ever make that worthwhile, because there's just too much radiation in space. In terms of bits, most people in quantum computing work still with what are called qubits, quantum bits. So they're still binary, but instead of being just 0 or 1, they can be superpositions of 0 and 1 at the same time.
With that, if we could thank our speaker one last time.